do you think? Give me some initial impressions. After reading this, hopefully it didn't put you to sleep. A lot of times these academic journals tend to be a little bit dry and a little bit blah, blah. That's the point. I mean, the point is, that's why I can't write them. I always get yelled at when I try to write an academic journal, so I write like I talk.
Is this the first article, right?
The first article, yes ma'am.
How come only 9?
Good! That's a great question. Now first of all, I want to answer that with a smoothing. 9's okay. You can do really good mathematically even less than 9 as long as you've got a good random sample. But let's go back to this question. How come only 9? Why do you think?
And they're all male.
Say that again.
And they're all male, too.
That's okay as long as that's your population, isn't it? No, that's a good thing. They're all male. They're all male, and that's okay as long as that's your population. As long as you're studying male cyclists, then you're okay to have all males. Good points. But why only 9? Why do you think? This isn't a math question. It's a practical question.
It's easy. There's only 9 kids.
I would hope that's not the case, although that's true, Deanne. Deanne said it's easier to stop at 9. Yes. That's easier than it costs less. Good. It might not cost. It costs less in much the same way fast food appears to cost less, though. And here's what I'm saying: if you do a study with 9, you have to accept a large margin of error compared to a sample of 90. The problem with that is you might have results where the error is exaggerated because of the large sample size, which you will then pay for with a retraction of your article later. Much in the same way that we think fast food is cheap, so we buy a lot of it, and then we pay for it with large health bills later. So I hope that's not the case. Sorry, I'm sorry. But I hope that's not the case. Go ahead, guys. Go ahead.
You go first.
You didn't say anything. Oh, I'm sorry. Where did you go?
There's more variables that you have to control for.
The problem is with elite male cyclists, every time you add an adjective to that, you make it more restrictive. Male cyclists, so that takes away half the field, assuming that there are equal numbers of male and female cyclists. I don't know if that's true or not, but you have to remove a bunch of the field. Now it's elite male cyclists. Well, how many of those are there? There aren't that many. And with EPO rules coming down, there are fewer and fewer every passing year. That's why I stopped watching in 04. Dan, go.
Does it say they're elite male cyclists?
If it doesn't in the actual part I captured, that was part of the actual article. This thing is pages and pages while I try to slow it down. Please.
Also, they're non-habitual coffee drinkers.
Non-habitual coffee drinkers, right? Tricky, Pacific Northwest, but we drink out here. Yes, so that's another adjective. Every time you add one of those descriptors, you're losing a pot of that population until you've got it down to non-habitual. Why would the non-habitual coffee drinkers?
Because they're going to have a tolerance to caffeine.
Because if we're studying the effect of caffeine, you would like to see caffeine against somebody that's not used to caffeine to see how it reacts physiologically perfectly. Thank you. Good. Kate.
Brings me what I thought was cool, that they did that, as well as that they did a double blind, and that they did the placebo 1.5 and 3.0. So
Excellent.
they did different sections to see how.
And how did they make sure that the system was getting flushed each time? I think it's in the second paragraph-ish. Provided 4 ounces of water and a gelatin capsule containing a placebo, 1.5 milligrams per kilogram, and 3. Each subject completed the 3 exercise cycles on a bicycle ergometer. After a warm-up period, 30 watts for 2 minutes, a pedal rate of 60 RPM was maintained, boom. For this phase, the workload was initially set at a steady state power for 5 minutes, then increased. So what they did was they put it's jargon, but they put these little spins in between each of those to make sure that the heart rate was able to come back down. All this talk of watts and RPMs is not important. What happens is, it's called interval training, a lot of ways, and this is interval testing, where they bomb out, and then they slow down. And then they bomb out, and they slow down. The slowing down allows the heart rate to come back to a baseline. So they're trying to establish a baseline each time. And on elite male cyclists, it's easy to do, because they're used to doing that. They're used to operating at a baseline level, and then pushing themselves out, and then bringing it back down, and then pushing. That's how you get stronger. It's much like bench pressing over and over again. You bench press, then you rest. And you bench press again, then you rest. That's how cyclists bench press and spandex on the plate.
And the fact that they also tested it the different, RPMs and not for different watts.
Yes.
It's not just, did this much caffeine affect at this rate? They're just saying, did these different amounts of caffeine affect them at different rates?
And that's the most interesting part. You almost have 2 different variables going on. You've got the level of exercise plus the amount of caffeine. Because what you wouldn't want to have happen is testing at one level of caffeine and having something spike at one level of exercise, and assuming that would happen at any level of caffeine. at that level of exercise. What you've done with making it at least 2 versus a control
And what they
is
said is that it didn't. So that
exactly.
showed
Except, and this is the, why are you reading this article? That's the next question I have.
you gave it to us.
Well, because I gave it to you. Why did I give it to you? Very good question, because I gave it to you and told you to read it. What's interesting? What's
Well, it's
interesting?
not what you expect.
Ah! Dan, say that again.
It's not the result you would expect.
It's an unexpected result. Let's hold that thought all day today, and while we're at it the next 6 weeks. You generally read in research articles about unexpected results, which means you're expecting something else to happen, but the opposite happens. You've just wrapped up in one sentence the whole point of what's called a p-value, which is what today and a bit of Wednesday is all about.
Well, aren't they all like that? I mean, we're not going to read an article, man throws apple up in the air, it fell.
But you
I
did a while
mean, you
ago.
know it's going to fall.
Unless for some reason somebody else decided to publish an article where an apple was thrown in the air and it didn't fall. And then you had to prove against that, showing more evidence against it. Now, that's an extreme example and an awesome one, by the way, an awesome one. But here's the deal. Remember I told you about that article, The Truth Wears Thin, last week? I think I mentioned this to you, where many studies are overturned, they can't be replicated. That's because some studies are in error. And it's, usually the ones that you see about that are in error are what are called false positives. We'll come back to that today. More on false positives today and types of error. Well, false positives can be very, 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 very bad. They can also be pretty innocuous. It depends on the context, which one of the things I want to talk about in this class for the next 6 weeks is which type of error is worse, a false positive or a false negative. Okay, we'll get to that. We'll get to that. But the idea is, yeah, you're not going to read the counter to Newton and the apple argument, but you might see a counter to an argument that says, you know what, this drug is totally fine for your liver, based on one trial of 40,000, and somebody else is like, all the anecdotal evidence points the other way. How did your trial show it did? For years and years, here's an example. Years and years and years and years and years. There was a urban myth that somehow multivitamins fought cancer rates. Okay, I didn't hear about this until relatively recently, but apparently it's been a commonly held belief, kind of like the inoculations give you more likelihood for other diseases. But, so multivitamins supposed to fight cancer rates, and for years and years and years, there's never been a statistical result that shows that. About a year and a half, maybe 2 years ago, a study came out that said they tracked a bunch of subjects for I think it was 40 years. Control group, experimental group, diet of multivitamins, not diet of multivitamins. Now it's tricky because it's a 40-year study. That opens up a whole can of worms like, okay, are they identical? I mean, you couldn't keep them in a lab for 40 years legally. So obviously they were out doing their life things. Hopefully they were all, let's assume the best, randomized, they were identical in every way. The problem is they were identical in every way, and in one way that unfortunately kind of negates the whole point of the study. Every single one of them was a white male doctor over the age of 50. So why does the headline say multivitamins fight cancer rates? It doesn't say multivitamins might fight cancer rates in white male doctors over 50, because that won't sell papers. I mean, that's the one study showing a positive test result when dozens and scores of studies have showed the opposite, but yet it makes the paper. You see what I'm saying?
Well, why don't they do a study about multivitamins get you into medical school?
That's a good one. Multivitamins get you into
How do
medical
they know that all
school.
those people are going to be doctors?
Well, that's a better question. They could have started testing them in medical school and then followed them, because they were all over 50 by the time the study was finished. So they could have very easily been in medical school when the study started, which wouldn't surprise me
But
one
it was
bit.
40 years, so they were over 10.
But they were over 50. They were over 50. They could have started it in their late teens, early 20s. The point of the matter is, as soon as I read that, I threw the study out because it was meaningless to me. So that's why you have to read deeply with all this stuff. Good, good. I like this study though, even though it's got a sample size of 9. Here are the results. Here are your results. I want to focus today on what these guys mean right here. These are the big guys, and we're going to start generating those on our own starting on Wednesday. But I've learned, at least I believe, that students benefit from one day, maybe a day and a half of actually analyzing just those numbers and what they mean versus calculating them and then understanding what they mean. It seems to almost make sense to get the number first. So, let's look at this study. This study has a research hypothesis. I don't know how it came about. What Dan said about we got something unexpected, we did. And chances are the lab wanted to get something unexpected. They wanted to show that caffeine did indeed lower heart rate. I mean, that's not the kind of thing you just wake up one morning and go, you know what? I think today when I drink my coffee, it's going to make my heart rate go down. That isn't the kind of thing you would just pop out of bed thinking. I mean, I don't think anyway. You would probably develop that idea somewhere else. Now, that somewhere else could be anywhere. That somewhere else could be observing other people. We're in a town like Bend, which is full of elite male cyclists. You might see a bunch of them in the middle of a ride, sitting in a cafe having coffee. You might think to yourself, why are they doing that? Why are they doing that? And being a cyclist myself, I might ask them. And they tell me, I think I can climb better on coffee. I'm like, really? You can climb better on coffee? Can you sprint better? No, I can't sprint better. But you can climb better. And then my mind starts thinking, if they can climb but not sprint, that uses a different level of exertion. Sprinting, you're going all out. Climbing, you're pulling back, but you're slightly above baseline. And eventually you might hatch a hypothesis based on that. Like, at mid-level exercise, caffeine seems to drop heart rate, where everything else it seems to raise it or not change it any more than normal. Does that kind of make sense? So we're going to have hypotheses we're going to be testing in the class, but it's not always obvious where they come from. I mean, where does polio vaccine come from? Chemical trials. You keep messing with chemistry until you come up with something, oh my god, this seems to knock down that little bacterium or that little virus. I don't know. Plague, is it a virus? I don't know what the hell it is. Whatever it is. It looks like it's kicking its ass. Let's test it against some innocuous strain and see if it works. There's no telling where inspiration for these hypotheses strikes. But this one we've got. So in this case, caffeine will significantly lower heart rate during and after certain levels of exercise. Notice they tested at 3 levels of exercise. Rest. Now rest for an elite male cyclist, you would laugh if you saw them. Resting does not look like resting. It looks like they're working their asses off. But for them, it's rest. It's a certain level of RPMs. Rest, sub-max, and max. So right below lactic threshold, you ever felt your legs like they're going to explode when you're exercising? Pedal on a bike, that you've crossed your lactic threshold, and now you have to stop because it's going to be really painful. They tend to operate, right, exactly. You can do it on almost any exercise. They tend to operate right below that threshold and try to raise that threshold. That's sub-max. And then maximal means you're right at it. You're burning. The null hypothesis is the opposite of the unexpected result. So the unexpected result is going to be phrased in the research hypothesis. I love the way you said that, the unexpected result. That's going to be phrased up here in the research hypothesis, i.e. caffeine is going to have some lowering effect on heart rate. That's unexpected. The expected result is caffeine is not going to lower heart rate. Now you can say that a couple different ways. You can say it doesn't lower heart rate, you can say it raises heart rate, but it's easier just to make it the exact opposite of what you're trying to see. If you're trying to see that it lowers it, say the opposite is that it doesn't lower it. That includes 2 things, doesn't it? If you say it doesn't lower it, it could stay the same, or it could increase. So you've got all that wrapped up in this one statement. And that's how I like keeping these binomial. Have what you want to see unexpectedly, and then have everything else. And then have everything else. Fair so far? So how do you decide which one you believe? That's how you decide. That gives you a tool, a decision engine. You feed data into a hypothesis test. And once you sausage grind out your data, it becomes a test statistic, which is paired with what's called a p-value. That's what today's all about. So we're actually going to skip the formal methods of hypothesis testing for today and go straight to the conclusions. And once we have the conclusions down tight, we're going to bump back to the actual crunching, if you will, sausage grinding of data in the hypothesis tests. But that bad boy is how you decide. That's what tells you, do I believe that or do I believe that? In other words, do I believe the unexpected or did the unexpected not show up? There's no guarantee the unexpected will show up. Generally, as I think Kate said, you generally read about the unexpected ones in the journals. And why? Because they're unexpected. Because they're unexpected. Nobody's going to publish a paper that says, yes, aspirin's still working. Because it does. It does. I mean, it would never get published.
Well, then even the ones that do say, the expected, so let's say someone counters this and says, no, caffeine really does higher,
Doesn't lower.
It doesn't lower.
How about that?
Okay.
Good.
The only reason they're writing that is because somebody else wrote one saying it does lower it.
Possibly. Quite possibly. And that's why I would want to see this replicated. Then your sample size 9 is not a sample size of 9. It actually increases and you get more precision. Yes. Or it falls apart. Or you learn that it falls apart. I've never checked this past this article, so I have no idea where it lives. Thank you for that. Renee, go. Please.
So the experiment is the science, and
figuring, like, inferring the results of statistics?
Yes. Pretty much the scientific method is statistical. Everything you guys have done in science class. I'm sure a bunch of you have done this before. Does the word null hypothesis ring a bell to some of you? Of course, yes. So you've done this before, and it was statistical in nature. The trick that doesn't sometimes happen, I was doing this in like 5th and 6th grade. We did an experiment where you get a bunch of plants, like I think bean plants, because they grow real fast, and half of them you yell at, "Rah!" And half of them you play classical music to. And then you let them grow, you do that for like a month. Every day you yell at one, and then you play classical music to the other ones. Then you check to see how they grew at the end of the month. Which ones grew more? The ones you yelled at.
The ones you put in the sunshine. I don't know.
They all had they're controlled for that. Controlled for that. They're right next to each other, except when we gave them the experimental stimulus.
Okay, I was wondering how.
Good. No, they're right. See, get in the light, then we break them apart. The ones you yelled at. Why?
Morons.
You're throwing carbon dioxide into them. That's what we figured. We figured the classical music sounds like it should be like a nice pleasant. But we're yelling at them, "Rah!" Which just throws carbon dioxide, which they love. That was our guess. Saw a hand. Where did it go?
And the p-value is how much?
The P. Hold that thought. You hold that thought. It asked a very good question about the p-value. Yeah, let's come back to that, if you don't mind. That's a fantastic. This is the point of, well, it's not on the slide. The p-value is the point of today. Thank you. Let's get into it. Okay? All right. Let's start.